Mount Baker rises above northern Washington like a frozen monument, its white glaciers and broad volcanic cone visible from towns, highways, forests, and even from parts of southern British Columbia on clear days. To many residents of the Pacific Northwest, the mountain appears calm, almost motionless, a permanent fixture towering more than 10,780 feet or 3,286 meters above sea level. Yet beneath that ice-covered summit lies one of the most closely watched volcanic systems in the United States. A volcano, the United States Geological Survey has formally classified as a very high-threat volcano because of the scale of danger it could pose if activity intensifies again. Why would a mountain that has not produced a major eruption in thousands of years receive one of the highest threat classifications in the country? Why are scientists paying such close attention to its steaming crater, unstable slopes, glaciers, and underground heat system? And why has Mount Baker recently become the focus of geothermal energy discussions at the same time federal agencies continue monitoring it for volcanic hazards? Those questions have become increasingly important as renewed attention falls on the volcano's geothermal potential and its long history of hydrothermal unrest. While Mount Baker is often overshadowed by more famous Cascade volcanoes, such as Mount St. Helens and Mount Rainier, federal hazard specialists have repeatedly warned that Baker's greatest danger may not come from a towering explosive eruption, but from massive landslides, lahars, rapidly melted ice, and debris flows capable of racing through river valleys with little warning. Mount Baker stands in Whatcom County, roughly 30 miles or 48 kilometers east of the city of Bellingham. It forms part of the Cascade Volcanic Arc, the chain of volcanoes created by the slow collision between tectonic plates beneath the Pacific Northwest. The volcano itself is relatively young in geological terms, probably less than 100,000 years old, although volcanic activity in the broader region stretches back far longer. The mountain's appearance often creates a misleading sense of stability. Thick snowfields and glaciers dominate the upper slopes, making Baker appear more like an alpine peak than an active volcano. But the ice conceals an intensely hot hydrothermal system beneath the summit area. Steam vents and fumaroles continuously release volcanic gases from Sherman Crater, a heavily altered section near the summit that has been the center of most modern volcanic activity at Baker. Sherman Crater became the focus of national attention during the mid-1970s, when Mount Baker unexpectedly showed signs of renewed unrest. Heat emissions increased dramatically. New fumaroles appeared. Ice around the crater began melting at accelerated rates. Scientists detected major thermal changes, and concerns spread across surrounding communities as authorities realized that even without a full eruption, the volcano could still produce destructive events. During that period, the amount of heat escaping from the crater reportedly increased more than tenfold. The glacier-covered crater began opening and expanding as snow and ice melted away under rising underground heat. Acidic water and altered volcanic rock created unstable conditions near the summit. Public officials temporarily restricted access to recreational areas near Baker Lake, while reservoir water levels were lowered because of fears that a large debris avalanche or lahar could surge into the lake system. Those concerns were not theoretical. Mount Baker's slopes contain enormous quantities of hydrothermally weakened rock. Over time, volcanic gases and hot acidic fluids chemically alter solid rock into unstable clay-rich material. Entire sections of a volcano can gradually weaken from the inside. If part of that weakened structure collapses, the mixture of rock, ash, ice, water, and mud can transform into fast-moving lahars capable of traveling many miles downstream. The volcano's extensive glacier system magnifies the danger. Mount Baker contains one of the heaviest concentrations of snow and ice in the Cascade Range. In fact, only Mount Rainier holds more glacial ice among Cascade volcanoes. 11 major glaciers descend from the mountain, feeding river systems that drain toward populated valleys. That combination of volcanic heat and massive ice coverage explains much of the concern surrounding Baker. Even moderate volcanic unrest could rapidly melt snow and glacier ice, unleashing floods and debris flows into river systems connected to downstream communities. Scientists have long emphasized that some of the most dangerous volcanic disasters in history were caused not by lava flows, but by lahars generated when volcanic activity mixed with water and unstable slopes. Mount Baker has already demonstrated its ability to produce enormous collapses in the past. Geological evidence shows that around 6,700 years ago, the volcano experienced a major eruptive episode that included massive flank collapse events and destructive lahars. Some of those mudflows traveled through the Middle Fork and Nooksack River valleys, while debris on the eastern side dammed the Baker River and helped create what later became Baker Lake. The evidence preserved in surrounding valleys reveals the scale of those ancient events. Some deposits from old lahars reached depths exceeding 300 feet, or about 91 meters, in upstream sections of river channels. Such events transformed landscapes far beyond the volcano itself. Despite this history, Mount Baker has not produced a major magmatic eruption in modern recorded times. That long, quiet interval sometimes leads the public to underestimate the volcano. Yet the United States Geological Survey threat ranking system does not rely only on eruption frequency. The classification also considers nearby populations, aviation hazards, infrastructure exposure, monitoring needs, lahar potential, and the likelihood that future activity could rapidly affect large areas. In Baker's case, several of those factors overlap in concerning ways. The volcano sits near transportation corridors, reservoirs, hydroelectric infrastructure, recreation areas, and populated valleys. Lahars, or major slope failures, could move through drainage systems connected to developed regions in northwestern Washington. The volcano also lies within a heavily traveled aviation region between Seattle and Vancouver, meaning ash-producing eruptions could disrupt air traffic across the Pacific Northwest. Even relatively small ash eruptions can create serious aviation hazards because volcanic ash particles damage aircraft engines and navigation systems. The mountain's glaciers introduce another layer of instability. Researchers have observed long-term glacier retreat across the Cascades as regional temperatures warm. On Mount Baker, glaciers advanced temporarily during portions of the 20th century, but have generally retreated in recent decades. As glaciers thin and retreat, they can expose unstable rock that was previously reinforced by ice. That process can increase the likelihood of landslides and debris avalanches on steep volcanic terrain. Combined with hydrothermal weakening inside the volcano, changing ice conditions create a dynamic and potentially hazardous environment. Recent discussions surrounding geothermal energy have further intensified attention on the volcano. In Washington state, officials, tribal organizations, and energy planners have increasingly explored whether Mount Baker's underground heat could someday support geothermal electricity generation. Several studies and planning efforts have examined the possibility of tapping geothermal resources somewhere on or around the volcanic system. One recent pre-feasibility assessment discussed the possibility of a geothermal facility capable of generating roughly 250 megawatts of electricity, an amount described as potentially approaching the power demand of most of Whatcom County outside major refinery operations. The interest is not surprising. Volcanic systems naturally concentrate heat closer to the surface, making them attractive targets for geothermal exploration. Steam, hot water, and underground heat reservoirs can theoretically be harnessed to generate electricity with lower carbon emissions than fossil fuel plants. But geothermal development around active volcanic systems also raises complex geological and environmental questions. Mount Baker's hydrothermal system exists within an active stratovolcano already classified as a very high-threat volcano. That reality creates a delicate balance between energy opportunity and hazard awareness. Federal land agencies have already examined geothermal leasing proposals connected to areas around Mount Baker. The United States Forest Service has reviewed consent to lease processes for geothermal exploration on national forest lands surrounding the volcano. At the same time, Washington state agencies have conducted workshops and collaborative planning discussions involving tribes, regulators, researchers, and energy developers regarding geothermal resources in the region. The renewed focus on geothermal energy has indirectly highlighted an important scientific reality. Mount Baker is not dormant in the conventional sense. the volcano remains thermally active. Steam vents continue releasing gases. Underground heat continues circulating through fractured volcanic rock. Hydrothermal systems remain alive beneath the glacier-covered summit. That distinction matters because many volcanic hazards do not require a large eruption. A destabilized hydrothermal system can trigger steam explosions, crater collapses, landslides, or sudden releases of hot water and debris. The history of Sherman Crater demonstrated that even increased heat flow without eruption can force emergency planning decisions. The mountain's geology adds to the uncertainty. Large portions of Baker consist of fragmented volcanic deposits, lava flows, breccias, and hydrothermally altered rock formed over thousands of years of eruptions, collapses, and glaciation. Unlike solid granite mountains, stratovolcanoes are often structurally fragile. They can fail catastrophically when internal weakening combines with earthquakes, magma intrusion, heavy rainfall, or hydrothermal alteration. Monitoring, therefore, plays a critical role at Mount Baker. Scientists use seismic instruments, gas measurements, temperature observations, satellite analysis, and deformation monitoring to detect signs of changing volcanic behavior. The monitoring network expanded significantly during the 1975 unrest episode, marking one of the first modern volcanic monitoring campaigns in the Cascade Range. Since then, Mount Baker has remained under continuous observation as part of the broader Cascades volcano monitoring system. Scientists are particularly attentive to earthquake swarms, changing gas emissions, rising ground temperatures, and shifts in deformation that could indicate magma movement beneath the volcano. One of the challenges facing researchers is distinguishing between ordinary hydrothermal fluctuations and genuine signs of magma ascent. Volcanoes often produce background unrest without erupting. Steam output can vary. Small earthquakes can occur naturally. Heat flow can change gradually over time. Determining whether those signals represent harmless fluctuations or early warnings of escalation requires long-term monitoring and careful interpretation. At Baker, scientists concluded that the unrest during the 1970s likely involved magma intrusion beneath the volcano that stalled before reaching the surface. The magma apparently heated the hydrothermal system without triggering a major eruption. That episode remains important because it demonstrated that Mount Baker is still capable of renewed magmatic activity. The volcano is not extinct. Its plumbing system remains active beneath the surface. Meanwhile, communities surrounding the volcano continue expanding. Tourism, recreation, hydroelectric infrastructure, transportation networks, and regional development all increase the number of people potentially exposed to volcanic hazards. Mount Baker's scenic reputation as a skiing, hiking, and mountaineering destination exists alongside its classification as one of the country's most dangerous volcanoes. The contrast is striking. On calm days, the mountain appears almost serene, with broad glaciers reflecting sunlight across the northern Cascades. Yet deep beneath those glaciers, volcanic heat continues circulating through cracks, fumaroles, and underground reservoirs. Steam escapes continuously from Sherman Crater. Acidic fluids alter rock strength. Snow and ice rest atop an active volcanic system whose future behavior cannot be predicted with certainty. The concern surrounding Mount Baker is not centered on a Hollywood-style eruption scenario. Scientists monitoring the volcano are more focused on the complex chain of hazards that could unfold even during moderate unrest. In many ways, Baker represents the kind of volcano capable of producing highly disruptive regional consequences without generating the enormous ash columns often associated with historic eruptions like Mount St. Helens in 1980. One reason involves the volcano's structure itself. Mount Baker is heavily fractured, deeply glaciated, and saturated with groundwater. Decades of hydrothermal activity have weakened portions of the volcanic cone through chemical alteration. Steam and acidic fluids circulating underground gradually transform strong volcanic rock into softer clay-rich material that can fail under stress. Once that process advances far enough, large sections of a volcano can become mechanically unstable. This is why scientists repeatedly emphasize debris avalanches and lahars when discussing Baker. A relatively small magma intrusion, earthquake swarm, hydrothermal explosion, or even gravitational collapse could destabilize weakened slopes and send massive flows of mud, rock, water, and ice into surrounding river valleys. The geography surrounding Mount Baker increases the seriousness of those hazards. Several major drainage systems originate high on the volcano, including the Nooksack River system and the Baker River watershed. Communities, roads, bridges, hydroelectric facilities, agricultural areas, and recreational infrastructure lie downstream from these valleys. Even if a future eruptive episode remained relatively small near the summit, lahars could travel far beyond the volcano itself. Historical evidence shows how destructive such events can become. During earlier eruptive periods thousands of years ago, debris avalanches and mudflows transformed entire valleys surrounding Baker. Some deposits buried older landscapes beneath thick volcanic sediment. River systems changed course. Natural dams formed. Lakes expanded or disappeared. These were not isolated summit events confined to the upper mountain. Modern communities now occupy many of those same lowland regions. Scientists are also concerned about how quickly volcanic hazards can escalate once unrest begins. The 1975 episode demonstrated that Mount Baker can change noticeably within a relatively short period. Steam emissions intensified rapidly. Snow and ice melted across Sherman Crater. Temperatures exceeded 266 degrees Fahrenheit or more than 130 degrees Celsius in some fumarole zones. At the time, authorities feared that continued heating might destabilize crater walls or trigger major flooding and debris flows. Reservoir operations were adjusted as a precaution. Monitoring systems were expanded. Access restrictions were considered around vulnerable areas. The eruption never materialized, but the episode fundamentally changed scientific understanding of Baker. Researchers realized the volcano possessed an active magmatic system capable of injecting heat upward into the hydrothermal network beneath the summit. That heat pulse was significant enough to melt nearly half of the crater's glacier ice during the unrest period. Even today, the fumaroles inside Sherman Crater continue venting volcanic gases. Under certain atmospheric conditions, residents in surrounding areas can see visible steam plumes rising from the summit area. During colder weather, condensation can make those plumes appear larger and more dramatic, occasionally sparking renewed public concern. Online discussions from Pacific Northwest communities often reveal the uneasy balance between familiarity and awareness surrounding Baker. Many residents have grown accustomed to seeing steam emissions from the crater, while others remain unsettled by the realization that magma-driven heat continues beneath the mountain decades after the 1970s unrest. Some local observers describe Baker as being in a long-term state of watchful monitoring, with persistent thermal activity but no immediate signs of eruption. That lingering thermal activity is one reason Mount Baker remains under continuous scientific surveillance. Monitoring efforts focus heavily on seismicity because rising magma usually fractures surrounding rock as it moves underground. Small earthquakes often provide the earliest clues that volcanic conditions may be changing. Researchers also monitor ground deformation. If magma accumulates beneath the volcano, parts of the mountain may slowly inflate or shift outward. Satellite measurements, ground instruments, and repeated surveys help scientists detect even subtle changes in surface shape. Gas monitoring provides another critical warning system. Changes in volcanic gas chemistry can reveal whether fresh magma is rising toward the surface. Carbon dioxide, sulfur dioxide, hydrogen sulfide, and other gases act as chemical fingerprints of processes occurring deep underground. At Baker, scientists regularly sample fumaroles and use airborne measurements to track emissions. The volcano's gas system is particularly important because Baker emits enough volcanic gas to be detectable through aerial monitoring, something not always possible at lower output Cascade volcanoes. Researchers have noted that elevated carbon dioxide levels at Baker strongly suggest continuing magmatic activity beneath the volcano. Scientists are also studying the chemistry and temperature of water draining from the volcanic system. Changes in water composition can indicate shifts in underground heat flow or magma movement. Even small temperature increases in springs, streams, or crater runoff can provide valuable clues regarding changes deep beneath the volcano. Another challenge involves the volcano's remote and heavily glaciated terrain. monitoring stations near Mount Baker must endure harsh winter conditions, snow accumulation, icing, avalanches, and difficult access. Some earlier monitoring infrastructure established after the 1975 unrest was later dismantled or reduced, prompting concern among federal agencies that the volcano still requires stronger long-term monitoring coverage. The United States Geological Survey has specifically identified Baker as one of the Cascade volcanoes needing enhanced monitoring because of the hazards posed to nearby populations and infrastructure. The Very High Threat classification reflects not only the volcano's geology, but also the potential societal consequences of future activity. Air traffic represents another major concern. The Pacific Northwest sits beneath heavily traveled commercial aviation routes, connecting major North American and trans-Pacific destinations. Even a moderate ash-producing eruption from Baker could disrupt flights across large portions of the region. Volcanic ash is especially dangerous to jet aircraft because fine particles can melt inside engines and damage critical systems. Mount Baker therefore occupies a rare position in the Pacific Northwest landscape. It is simultaneously viewed as a natural landmark, a recreational destination, a water source, a volcanic hazard, a geothermal resource prospect, and a continuously monitored geological system. That combination explains why scientists continue paying close attention to the volcano despite its long eruptive silence. Baker's glaciers, hydrothermal activity, gas emissions, unstable slopes, and underground magma system all point to a volcano that remains alive beneath the ice. Steam still rises from Sherman Crater. Volcanic gases still escape through fractures near the summit. Instruments still scan for earthquakes and ground deformation. Researchers still measure water chemistry and heat flow for signs of change. The mountain dominating the northern Washington skyline may appear quiet from a distance, but the classification assigned by the United States Geological Survey reflects a very different reality beneath the surface. Mount Baker remains one of the most closely watched volcanoes in the United States, not because scientists expect imminent catastrophe, but because the geological ingredients for dangerous activity continue to exist inside the volcano today.